I do. All right, here we go. So this is the beginning of Unit 5. So this is Unit 5, Part 1. And that is just solving trig equations. Today, we're going to stick with some pretty basic trig equations. So this is 5.1 today, and this is basic trig equations. We're going to start simple. Today, we're just going to focus on things like can we isolate a variable on one side of an equation? Can we use a square root to solve an equation? Can we use some basic factoring out of GCFs to solve an equation? Those are the kinds of things that we're going to go for. I want to talk a little bit about just some really simple equations, something like sine of x equals the square root of 3 over 2, and the cosine of x equals negative square root of 3 over 2. I want to talk about those for just a minute. So these we sort of discussed a little bit in the last unit, kind of intermixed within some of the other things that we were doing. But the idea with these is we are trying to find the angle that would give us a sine of radical 3 over 2, or the angle that would give us a cosine of negative radical 3 over 2. The thing I want you to remember about trig equations, and this is probably one of the most important things to remember, is that your unknown is an angle. This is what you're solving for. We are trying to figure out an angle. That's our goal. So if we can find out what angle gives us a sine of radical 3 over 2, we've solved that equation. So let's practice with that a little bit. This is kind of what you're shooting for in every trig equation is something that looks like this. The trig function all by itself and some expression that's a number on the other side. That's our goal. When we get it to that point, we can think about, well, what's on our unit circle? So thinking about this angle, what angles, and that's why I'm writing x now, what angles have a sine of radical 3 over 2? So on your unit circle, where do you have a y value that's radical 3 over 2?
60 and 120.
Okay, good. So you have 60 degrees. That's the first angle in quadrant 1. And then also in quadrant 2, we know because of all students take calculus that in quadrant 2, sine will be positive as well. So we have to find the angle in quadrant 2 that has the reference angle of 60 degrees, and that's 120 degrees. So those are our two angles in degrees. What if I ask you to write those in radians? What's 60 degrees in a radian measure? Pi over 3. And then 120 is 2 pi over 3. Good. So we could write our angles either as degrees or radians. You will be given specific instructions in how to write your answers, and I'll talk about what that looks like in just a second. So let's just try this one too. So we have the cosine of x equals negative radical 3 over 2. So now we're trying to figure out what angles have an x value, cosine, of negative radical 3 over 2. So put yourselves in the right quadrants first. Where is cosine negative? 2 and 3. So we're looking for angles in 2 and 3 that have a x value of negative radical 3 over 2. So what angles have an x value of radical 3 over 2? Think in first quadrant, which ones would that be? Or which one, I guess?
5 pi over 6.
Okay, so you're going into second quadrant. Good. So 5 pi over 6. I like it. And so that's second quadrant. We want quadrant, what did we say, 2 and 3? 7 pi over 6, right? And we said quadrants 2 and 3, I'm going to write that here. Quadrant 2 and 3. Right? Because it's a negative cosine. Okay, so what are my angles then? So what's the reference angle? Oh, I said 3. It should be 6. Sorry. I wrote 3 and that should be 6 here. What are the reference angles when we have a denominator of 6? So in quadrant 1, what's your angle that's pi over 6? 30, right? So we're talking about reference angles that are 30. In quadrant 2, we're less than 180. So 30 degrees less than 180 is 150. 30 degrees more than 180 is 210. Okay? So I could give my answers either in degrees or radians. Those are my options. All right. How do I know how to give my answers? That's the second question we need to kind of discuss here. So we're either going to see give your answers between 0 and 360 degrees, or between 0 and 2 pi. So if you see it written as this, how do you think I should give my answers? So this first one. In degrees, right. So degrees for here, answers in degrees. What about the second one? In radians, right? And you have to look for that because it should tell you in the beginning to give your answers in one way or the other. If it doesn't, then you can give it however you want. Notice also, I include 0. So I say 0 is part of my solution set. But 360 degrees and 2 pi are not. Everything up to those two, everything up to 360 is fine. But once we get to 360, we don't include that as part of our solutions. All right, so let's make it a little bit more challenging. We're going to try a few strategies here. 3, actually. So our first strategy is going to be just to collect like terms. All right, so that's strategy number 1. What we want to do is get all of the like terms on the same side of the equation, and then hopefully from there we can isolate whatever our trig function is. So that's going to look something like sine of x plus square root of 2 equals negative sine of x. All right, so if I want to collect my like terms, bless you, sine of x and negative sine of x, those are like terms. So if I want to collect like terms, what I'm saying is I want those two things to be on the same side of the equation. So any ideas how I could make that happen? What do you think? Add sine of x, yeah. Let's add sine of x to both sides. Okay. So if I'm saying take sine of x and add another sine of x to it, how many sine of x's do I have? 2. So I have 2 sine of x plus square root of 2 equals 0. Because negative sine of x plus sine of x is going to be 0. Now this isn't bad, it's better, but now I want to try to find a way to isolate this sine of x. I want to try to get just sine of x by itself. So what do you think I should do? I like it. Let's subtract square root of 2 from both sides. Okay, I feel like we're making some progress here. Remember, I'm trying to get sine of x by itself. That's my kind of first goal here. So now what? Divide by 2, yeah. Let's divide both sides by 2. Now I've got sine of x by itself. That's pretty helpful. Because remember, my unknown, my x, is an angle. I've got to figure out what angle has a sine value of negative radical 2 over 2. And if there's more than one angle between whatever I'm being asked to give my angles as, let's say I want to give my angles, we'll say this time in degrees. Okay, so let's give our answers in degrees. I need to find the 2 angles in degrees that have a sine of negative radical 2 over 2. So think about your unit circle. Sine is y. What's our reference angle for radical 2 over 2 for sine and cosine? 45. So we know we're dealing with our 45-degree reference angles, right? So now we have to think about what two quadrants are we in? 3 and 4. So we have a 45-degree reference angle in quadrant 3. So that means we add 45 to 180 to get what? 225. And then in quadrant 4, we have to subtract from 360, right, and we get 315. And those are our two answers. So the process is isolate that trig function and then use your unit circle knowledge to help you find the actual solutions. Our solutions are what x is, okay? All right, so our first strategy was to collect like terms. Our second strategy, any questions on that one before we go on to our second strategy? All right, is to use square roots. That's our second strategy. Let's see, the equation I want to use for that one is 3 tangent squared of x minus 1 equals 0. There are a couple of ways that I can write this idea of a tangent being squared, because we haven't yet seen a trig function being squared. That's kind of weird to think about. So we have to make sure we understand what exactly that is telling us is happening. So maybe you could rewrite it like this, and it might be a little more helpful. Okay, we're thinking about the tangent function. This whole thing is being squared. So we would find the tangent of whatever x is and then square it. All right, so I want you to think about that being tangent squared. You'll see the equations written this way, the way I wrote it initially. You can rewrite it if you'd like, or you can just work with it in its original form. I don't care, whichever one makes more sense for you. But I want to figure out what the solutions to this equation are. So once again, I've got to get this tangent of x. I'm trying to isolate this. So what do you think I should do first? Okay, I heard lots of good ideas here. And they're all going to be something we're going to do along the way. But I have to remember when I'm solving an equation, I have to undo what's being done in reverse order of operations. That's what it means to solve an equation. So if I were to plug in x, the first thing I would do is find the tangent, then I would square it, then I would multiply by 3, and then I would subtract 1. So the last thing I do in order of operations is the first thing I undo. So the first thing I'm going to undo is adding 1 to both sides. Oh, I almost caught it. Okay, so let's add 1 to both sides. You guys had some good ideas in there we're going to use as we continue to move forward here. So now, if you think about your order of operations, we would plug in x, we would do the tangent of x, then we would square it, then we would multiply by 3. So the last thing I do in order of operations is the first thing I would undo. So I'm going to divide by 3. All right, so now I've got, don't forget the x, tangent of x squared equals 1 over 3. Now what do you think I should do? Take the square root. Now this is where we need to be very careful. So we're going to take the square root of both sides. When we take the square root of both sides, is there just one answer? No. We always have to remember that when we take the square root of both sides in an equation, there's actually 2 answers there, plus or minus square root of 1 over 3. When you see a squared in the equation of a trig equation, a lot of times, well, not a lot of times, everywhere, that means you're going to be multiplying the number of solutions you would normally find by 2. You're going to find twice as many solutions. So let's really dive into what this radical or square root of 1/3 is. Because I think if we're being honest, this is not something we're used to seeing when we talk about the value of tangent. So let's work on simplifying that a little bit. So let's simplify, and I'm not going to simplify it all the way. Plus or minus the square root of 1/3. What I am going to do is try to make it something that looks like what we're used to seeing on the unit circle. So when I have the square root of a fraction, I can take the square root of just the numerator and the square root of just the denominator. Now let's think about what is the square root of 1? 1. Can we do the square root of 3 nicely? No. No. Okay, I'm going to leave it just as the square root of 3. Now I know everything in you right now is going, oh, I should rationalize this. Well, yeah, if this was your answer, absolutely. That's not our answer, though. Remember, what we're doing is we're solving this equation. Tangent of x equals plus or minus 1 over radical 3. That's what we're trying to solve. We're trying to figure out what angle has a tangent of either positive 1 over radical 3 or negative 1 over radical 3. The reason I'm not rationalizing it is in pure form, when we take the values from the unit circle, it's not rationalized. We do the rationalization at the end so that we have like a standard form for our answer. But I have to think about this as when I just pull the stuff from the unit circle, this is what I get. Now, if you remember, I talked about the unit circle, how everything that has a denominator of 2, we can sort of ignore the denominator of 2 when we're doing tangent. So for instance, if I was looking at 30 degrees, the radical 3 over 2 and the 1/2. If I wanted to find tangent or cotangent, I can just focus on the radical 3 and the 1. I can just focus on the numerators. So let's look at our first quadrant and see if we can figure out at least what the reference angle is for this. I've got to do y divided by x, that gives me 1 over radical 3. Well, if we just start with the first angle in the first quadrant, I have a y value with a numerator of 1 and an x value with a numerator of radical 3. That's exactly what we wanted. So here's what that tells me. That tells me my reference angle is going to be 30 degrees, right? So I know I'm dealing with 30-degree reference angles. So I can say, well, for sure, 30 degrees is going to be 1. Now, I want plus or minus. I want positive or negative tangent. How many quadrants have a positive or a negative tangent? All 4. So we're going to write down all of the reference angles for 30 degrees. So 30 degrees, then what? 150, good. Then what? 210, and finally 330, yes. So that would be in degrees. What if I ask you to give me the answers in radians? So let's just for fun find our answers in radians. What's our 30-degree angle in radians? First, let's start with the denominator. What's the denominator for all of these going to be? 6, right? Because all of them have a reference angle of 30, which means all of them will have a denominator of 6. So first quadrant, what's the numerator? Pi. Second quadrant? 5 pi. Good. Third quadrant? 7 pi. Oh, yeah. Go. 11 pi. Good. Okay, these would be in degrees. Oh, I'm sorry, in radians. So this solution actually has 4 different solutions. There's 4 different angles here that we would say are solutions to that original equation. If we pick any one of these angles and put them back up here in the original equation, right here or here, if I put in 30 degrees here, tangent of 30, we just said is 1 over radical 3 squared, would be 1 over 3, times 3 is 1, minus 1 is 0. Okay, so it makes that equation true. Okay, so that's 2 of our strategies. We've got one more. And the last one, I'll say we're just going to use the zero product property with GCF. Kind of, believe it or not, that's abbreviated. There's trying to get the main ideas here. We want to use a zero product property in conjunction with looking for a greatest common factor. So we're going to do 2 of these. I'm going to do them not side by side this time because I did them side by side earlier and it got a little confusing to look at. So sine squared of x equals 2 sine of x. I'm going to solve that equation. Let's just give our answers this time between 0 and 2 pi. So that means I want my answers in radians. So we're going to use some of the strategies we've already talked about, like getting like things on the same side. Now I have to be careful with how I say that because these aren't like terms, but they both have a trig function in them. So they're similar in nature. I want to get everything in this situation that has a trig function in it on the same side of the equation. That's generally going to be my approach. So what do you think I can do to maybe get this 2 sine of x on the same side as sine squared of x? What would we do with that? If I wanted to move 2 sine of x to the other side, dividing it would give me a 1 here, and then I'd have a fraction. I don't like fractions if I can avoid them. Subtract, yeah. So let's subtract it. Now, we're not going to be able to combine these two things into the same term because this is sine squared, this is not. All right, and that's important to understand. It's like saying x squared minus 2x. We can't combine those into a single term. They're not like terms. They both have x's in them, but they're not like terms. I'm going to rewrite sine squared as this also in this step. You don't have to, but I do think sometimes it helps you to see a little bit what's happening just a little bit better here. All right. Now, our hint is our strategy. Last thing in our strategy says GCF. Looking at these two things, they have something in common. And what I like to kind of compare that to is this. If I had x squared minus 2x equals 0, you would factor out what? The x. Oh, that was you. I thought I was looking at the wrong person. X minus 2 equals 0. Why do I factor it? What does that allow me to do then? My goal being solving for x. How does that help me solve for x? What do you do? Go ahead. Yeah, and I do that by setting each of these equal to 0. That's kind of what I was looking for here. Because this process of setting things equal to 0 when I've got them factored is using the zero product property. The zero product property literally says if you're multiplying two things together, which we are right here, whoops, multiplying those two things together, and it is 0, then at least one of the two things has to be 0. That's why we set them equal to 0 like we do. So I want to use this idea, but with my trig functions. So when I look at my trig functions, sine squared minus 2 sine of x, what do they have in common, those two terms? A sine of x. So I'm going to factor out a sine of x. I'm going to write that. Because I think it's helpful when we look, if you look back at this later, to kind of see what we did. So let's factor out a sine of x. That means I have to think about if I were to redistribute the sine of x. Okay, I have to get what I started with. So if I were to multiply this out, I have to be able to get this. That can help you factor it. So what am I going to multiply sine by to get sine squared? Sine, absolutely. So we have sine of x here. What would I multiply sine by to get negative 2 sine? Negative 2, so minus 2. We just factored an expression with trig functions in it. Now we can use the zero product property. Okay, so I'm going to use the zero product property next. And set each thing, so set this guy and this guy equal to 0. So that's going to give me two equations. Sine of x equals 0 and sine of x minus 2 equals 0. So basically we're going to use the same strategies that we've been using to now solve these equations. So if I have sine of x equals 0, remember what I'm trying to look for here is what angle has a sine of 0. So when do you have a y coordinate that is 0? 0 and 180. And remember I said I want us to give them in radians this time. So x equals 0 because 0 and 0 degrees are the same thing. But what is 180 in radians? Pi. Okay, so we have two solutions there. Let's talk about this one. What do you think I should do to get sine of x by itself? Because that's my first goal. Get this guy by itself. Add 2. Good. So let's add 2 to both sides. So I get sine of x equals 2. Now, here's the thing. Do we know of any angle on the unit circle that has a sine of 2? Absolutely not. That does not mean that there isn't a solution for that equation. Okay, it could just mean there's not a solution that is including any of the special angles that I have, right? The chances of getting one of those, what is it, like 16 angles, is pretty small when you consider that there's 360 degrees in a circle, okay? So it doesn't mean that there's not a solution. It just means that there's not a solution that we can see with our unit circle. We'll talk about how to address that. But I want to even go a little bit further with that. It is possible that there's no solution from this equation. And that's going to happen in some pretty special situations. Let's think for a minute about what's the ratio for sine? Opposite over hypotenuse, okay? So sine of any angle is the opposite side over the hypotenuse. So if we think about that in what we have, that would be 2 over 1. So this would be the opposite side, and this would be the hypotenuse. What do we know should be true about the hypotenuse in a right triangle? What has to be true about the length of a hypotenuse in a right triangle? And what, even go a little bit further than that. When we say C always has to be what, not the hypotenuse, but talk about the length. Yes. Hypotenuse has to be the largest side in your triangle. If it's not going to form a triangle. So, if we know that the hypotenuse has to be greater than the opposite, what does that tell us about our situation here?
It's not possible.
It's not possible. Because we have a smaller hypotenuse than the opposite side in this expression. So I would say in this one that this has no, oops, somehow I ended up on highlighter. This one has no solutions from it. Okay, now that doesn't mean we don't have any solutions at all. It just means that that part of the equation doesn't lead to any solutions. However, we do have two solutions here, 0 and pi. If we put those back in the original equation, we're going to get a true statement. Okay, let's try one more. And then we should be done. So last one. So if I take cotangent of x times cosine squared of x equals 2 cotangent of x. I want to solve that equation. All right. Just like in the previous example, I want to try to get all of my trig functions on the same side. Okay, it's kind of like most of the time going to be a good first step. So how could I get all of my trig functions on the same side? What should I do?
Minus 2 cotangent of x.
Good. Let's subtract 2 cotangent of x. Now here's where we have to be careful. A lot of people see this and they're like, oh, okay, well that would just be negative 2 cosine squared of x. You got to be really careful about that. This minus this, these are not like terms. They have similar things in common, but they're not like terms. So I would just have to write that as cotangent of x, and I'm going to write cosine squared again the other way, just for now, minus 2 cotangent of x. So I'm just going to subtract those two things. Now, keeping in mind which strategy this is under, okay, we're going to use the zero product property with GCF, what do you think I should try to do here? Any ideas? What do you think?
Do you do cot x equals to 0 now?
Okay, you're on the right track. You kind of skipped a couple steps, but yes, we are going to do that, absolutely. The way I'm going to achieve that is, look, I notice there's a cotangent of x in this term, there's a cotangent of x in this term. That's a GCF.
Oh, okay.
So let's factor that cotangent of x out. And then once again, we have to think about what's going to be left. So I would have to multiply cotangent of x by something to get cotangent times cosine squared. What would that something that I would multiply cotangent by be? Cosine squared, good. And then what would I multiply cotangent of x by to get 2 cotangent of x? Yep. So really, when you identify what your GCF is, most of the time, if you cover it up, you'll kind of see what you're going to have left. Go ahead.
Oh wait, never mind, sorry. I just realized my mistake. Hang on.
Okay. We have to be careful in this situation not to divide by cotangent at the beginning here. A lot of people want to do that, and the reason we can't divide by cotangent is we might actually end up dividing out a solution. But now we can use the zero product property. Okay, I'm going to take this guy, set it equal to 0, take this guy, set it equal to 0. So that's going to give me cotangent of x equals 0 and cosine squared of x, keep writing it the same way, minus 2 equals 0. Okay, solve that for x. So start with the first equation. We're looking for when cotangent is 0. So we know on the unit circle cotangent is what over what? What two things do we divide on the unit circle with cotangent? Adjacent, an opposite, yes. Good, I like it. Adjacent and opposite, put it in terms of the unit circle. So what part of your coordinates are you dividing there? We're doing x over y, right? Did you say that or did you say the opposite?
I said 1.
Oh, okay, I don't know who said that. Yeah, it's x over y. Y over x is tangent. X over y is cotangent. So we're looking for, we have to think about this. We need, from our unit circle, we need an x over y that ends up being 0. So that could either be 0 over 1, 0 over negative 1, it could be 0 over 5, whatever. Our numerator just has to be 0. That means our x coordinate has to be 0. So think about where on your unit circle you have x values that are 0. Yeah, 90 and 270. So let's do degrees this time. So we'll just do 90 and 270. Okay? Awesome. We've got 2 of our solutions. Maybe there's more. Let's see. So what do you think I should do first in this second equation? Add 2. Good, I like it. So we're going to add 2 to both sides. Then what? Square root. What do I have to be careful when I take the square root of doing? Plus or minus. Good. All right. I know you're seeing, oh, it's a square root of 2. Awesome. That's on our unit circle, but we have to be careful. This is the cosine is the square root of 2. We have to think of it as square root of 2 over 1. Right? Because it's not a fraction. In order for us to think in terms of the unit circle, it'd be helpful if it was. What's the ratio in terms of opposite, adjacent, and hypotenuse for cosine? So what over what for cosine? Yeah. I think you said maybe tangent? Adjacent over hypotenuse? Yeah. So just because we don't see it on our unit circle doesn't mean there isn't a solution. I'm going to check to see if there's a solution. What do I notice about this again?
Hypotenuse is less.
Yeah. So our hypotenuse is less than the adjacent side, which tells me there's no solution for this one. for now, if there isn't a solution on the unit circle, but there might still be a solution, I don't think I have any of those on this first assignment. You can kind of address those. We'll address them in class if it comes up. But I want you to find any solutions on your unit circle for now. Okay? Any questions on this? Okay, so remember, the most important thing from this is to remember that your adjacent side, or not your adjacent side, sorry, your unknown is an angle. That's the whole point of this process, is identifying what angle makes that equation true. So we're solving for an angle, okay? All right.